So what we want to do for this section is try to visualize 3 dimensions, and the way to get it down on paper is 2 dimensions, and so we're trying to visualize 3 dimensions. We can see in 3D, but we want to transfer what we see in 3D down to 2 dimensions on our paper. And we also want to identify some basic equations in 3 dimensions and identify the coordinate planes and things like that. And then part of what you guys did in the lab were some distances in 3 dimensions also, and like midpoints and stuff like that. So let's try to jump into doing stuff like that. In 3D, what we want to do is we want to draw something 2-dimensionally and try to make it look 3-dimensional by looking at it in perspective, in a certain perspective. So one of the things that you'll be doing a lot is drawing 3-dimensional axes. And if you draw it in a certain way, you kind of make it look like 3 dimensions. You kind of make it look like one of the axes is coming out of the board or out of your paper if you draw it a certain way. So in general, we want to draw our axes with an X, Y, and Z in this way. And it would be nice sometimes to be able to rotate this around and be flexible with rotating it around. But there's a certain order to drawing your X and Y and your Z. And it kind of follows this idea of a right-hand rule. So if I redraw and rotate my axis so that this is my X, now which one is going to be my Y and which one's going to be my Z? So the top one is Y and then this one is Z. So the idea behind the right-hand rule is that if you take your right hand and you wrap your fingers in the order what? Is there a problem? You wrap it around going through the X axis first and then the Y axis. If you're using your right hand, then your thumb would be going in the direction of the Z axis. So over here, if this was your X, if you were to wrap your finger, your right hand, going this way, if this is your right hand, then your thumb has to be pointing down, right? So that's not going to work. So what you need to do is you need to wrap your right hand around this way so that your thumb will be pointing in the direction of the Z. So it has a counterclockwise direction, looking at it from the top. Okay, so that's the right-hand rule, and that's how you can distinguish which one is which axis. Okay. Let's take a look at some more information about the 3-dimensional coordinate axis. It's a 3-dimensional coordinate axis with an X and a Y and a Z, and so we can define points in X, Y, and Z. So we can, for example, define a 1, 2, and a 3 as a point. And when we do that, we can start from the origin, just like we could do it in 2 dimensions. If we do the first 2 dimensions, X and Y, we can imagine it going along the X-axis. And so some tricks of drawing things in X and Y axis, usually if you look at the XY plane, we think about that as being the floor And if you want to draw lines that are parallel to y or lines that are perpendicular to x, then if you want this to be perpendicular looking to x, you would draw it parallel to the other big line that's perpendicular to x, and that's the y-axis, right? So I would draw that perpendicular to the y-axis so it looks like it's going along the y, and as it should be. So this is 1 unit in the x direction. Now 2 units in the y direction, again, I would want to draw these tick marks to be, I want it to be parallel or perpendicular to the y-axis, so it should kind of be parallel to the x-axis. And 2 units this way would give me my 2 units in my y direction. So what I want to do is I want to draw a line that's parallel to those axes, and then this would give me my point 1, 2 on the xy plane. And the fact that it's on the xy plane says probably my third component z is 0 at this point, so I haven't made it gone up yet. I'll make the z go up in 3 units in a minute. To get my z-axis, now I would just probably draw this perpendicular to my z-axis. And then what I would want to do is I would want to draw this line segment and try to measure that line segment and then move it to where you're drawing it from the z. Now, notice it's not going to be the same height as the 3 units in the z-axis because it's a little bit lower. But this is going to give us our 3-dimensional point, 1, 2, 3. And so with each point, you kind of make a box from the origin. And you don't need to draw this all the time. In fact, it would probably be a little bit tedious to draw this all the time. But you get to make a box from the origin where the opposite diagonal is going to be the point that you're looking at. Okay? So now we're looking at space. Not just the plane, 2-dimensional plane, we're looking at 3-dimensional space. So these spaces are separated by, you know, the 2-dimensional plane is separated by the axes, right, the x and y axis, and it separates it into 4 quadrants. So now, if we're in 3 dimensions, the separation is going to be done not by the axes alone, but by actual planes. So the coordinate axes are going to be represented by special planes. So coordinate planes if we look at the x, y, z space like this, we could take a look at the coordinate plane where, well, the xy plane. That's passing through where the x and y axes are actually intersecting it. So what can be said about all the points on this plane? So regardless of where you are in x and y, z is always going to be 0. So if I pick a point here, like 1, 2, this would be 1, 2, 0. If I pick a point on the other side over here, like maybe positive 1, negative 1, positive 1, negative 1, 0. So the idea there is that the z value is always 0. So I can essentially describe all the points on the x, y, z space where z is equal to 0 as the x, y coordinate plane. Notice that the xy coordinate plane has a z that's equal to 0. And so if we kind of take that logic along with us, the yz coordinate plane can be described as how? Take a guess? X equals 0. And then similarly, the zx coordinate plane, or xz, is your y equals 0 plane. Okay? Let's take another look at maybe something that's not 0. What if we take a look at z is equal to 1? So give me some examples of points that would be on this z is equal to 1 relation. 0, 0, 1. 2, 3, 1. 4, 2, 1. You guys are all positive. Square root of 2, 1. Okay, so notice that these are all points that we can take a look at. They have different x and y values, but the z is always going to be equal to 1. So what we could do is we can imagine how this would look like. And to try to draw this is kind of tricky because when you draw it, it might look like it kind of looks like this plane over here. So the trick to make it look like it moved up 1 unit, because that's what's happening, is that it's parallel to the xy plane, but it moved up 1 unit. So to make it look like it moved up 1 unit, maybe you can just make a little mark over there saying it moved up 1 unit. Or maybe draw it a little. Whoops. So that z is equal to 1. What do you mean by line? Yeah. Which one center is the z-axis?
The ones that move up at the corner at the point where z is 1, and otherwise not have it exactly on the point.
Like this? No, I don't know. You guys can draw it any way you want. Maybe we should take those clicker things out. Just came up with an idea. Oh, but you can't look. All right, let's try this. All right, let's see. So take a look at it. The x and the y-axis are the arrows that are pointing in the direction. The z is going straight up. And let's see if I can do this. So I'm going to call out a color. I know, kind of changing colors. Maybe I'll point it out. So I'll call out a color, and then you have to tell me if the answer is A, B, C, or D. All right. All right. Which one is the red graph? This one up here.
That's red.
Yeah, sure. You're supposed to don't say what the answer is. Figure out it's A, B, C, C.
I just.
All right, ready? Let's see. Susanna, you get your finger out. Okay. Victor, you're right behind me. Okay, got you. Okay. All right, the next one is, I'm going to say the purple graph. This is the purple graph right here. I don't know, just whatever this graph is. Whatever color you want it to be. All right, you guys got your answer? Yep. Okay. Okay, you guys have your answer?
Wait.
Let's try. And then we'll do one more. So this one is the blue. This graph right here. It turns purple every once in a while. Brown, purple. It's not turning blue. It's blue. It's just a protector. Is that dress black and blue or white and blue? All right, this is that one, yeah? Two. Okay. Stop moving it. Okay. Alright. Make this with your fingers on it. Yep. Okay. Thanks. That was fun. I think I need to prepare this. All right. So if I freeze it right there, I think the colors are fairly. So z is equal to 4 as the red graph that's up high. The green graph down here is z is equal to -3. The blue graph, I told you it was blue. Well, it looks bluer on my computer. this graph over here, the blue graph, is x is equal to -3, and this purple one, what I meant to be purple, is y is equal to 1. Brown. Is this pink? Yeah. Yeah, this is supposed to be purple, and it's supposed to be this one right here. What? I don't think they have brown. Oh, I should have done like groovy colors.
Rainbow. That would have been perfect. That would have definitely helped.
All right, next time.
Or yellow too. Oh, yeah.
Really? It's yellow. Ah, whatever. Okay. We're just shooting the breeze here. Basically, these graphs are parallel to coordinate planes. That's what it really kind of boils down to, right? So, for example, this first one is parallel to the x equals 0 graph, which is the YZ coordinate plane. And it just gives you a different x value of -3. Instead of x being 0, it gives you an x value of -3. This is supposed to be a 0. And so, similarly, all these other ones are going to be parallel to the other coordinate planes. So this is parallel to the xz plane. And then these two are parallel to the xy plane. Okay? So we'll see these a lot, especially when we start studying surfaces in 3 dimensions. We're going to say something that's parallel to the xy plane, that's cutting a surface or something like that. So we have to kind of be able to visualize these planes that are happening. All right. So those are some of the coordinate plane ideas. Maybe I should have followed my notes a little bit. Oh, let's take a look at some equations and see what kinds of other things they might describe. We've talked about these equations that x and y and z are equal to constants, but now we can start combining them and get some idea of how they might look like. Now, we have to remember that we're trying to visualize these things in 3 dimensions. And so what we want to do is we want to imagine how they might look like in 3 dimensions. And in 3 dimensions, we're looking at points x, y, and z. I know when you're looking at that first example, it looks like it's just something on the xy plane, right? And so imagine this thing being on the xy plane, and what we're saying here is that it doesn't matter. It doesn't matter what z is equal to, you're always going to have the same relationship between x and y. So we want to try to draw this in 3 dimensions. And what we know for sure is that on the xy plane, if we were just looking at this on the xy plane, we get a circle. So now let's imagine picturing the circle on the xy plane in 3 dimensions. And we have to kind of draw the circle a little bit slanted because we're pretending that we're looking at it at an angle. But what does it mean when we're missing a z variable and we're saying that it doesn't matter what z is equal to, the x and y coordinates are always going to be the x and y coordinates. They're always going to have the same relation. What can you say about this thing? You get like a cylinder. So you can get the exact same figures with different z values. Maybe I'll just copy and paste it. So what we could say is that it doesn't matter what the x and y, it doesn't matter what the z is, the x and y is always going to generate a circle. So at some level z is equal to 0, you get a circle. Z is equal to 1, you get a circle. Z is equal to -1, you get a circle. Z is equal to whatever, you get a circle. So eventually what you'll get is a bunch of these circles that would eventually become solid if you sweep it up and down. So that's an important thing to try to remember now, is that if you're trying to describe things in 3 dimensions and you notice that one of your variables is missing, and what you can do is think about drawing whatever shape this is supposed to look like in the plane that it belongs to, and then sweeping that along the missing axis. We're missing a z variable here. We're going to sweep it along the z-axis. So you got that idea? It goes to infinity in both directions. I stopped. It looks like I stopped here, but really it goes on forever. Just like a line goes on forever, just like a plane goes on forever. This is a cylinder that will go on forever. All right, so let's try to apply that same idea to these other graphs. Y squared plus z squared is equal to 1. What do you think of there? It's a circle. Circle on what plane? On the YZ plane, right? So on the YZ, I would draw a circle. And then the missing variable is x. I would sweep it along the x. Oops. No. I want it parallel to the x-axis to make it look like I'm sweeping along the x-axis. And again, it goes on forever on both sides. So this would be a cylinder going along the x-axis. How about x is equal to z squared? How would that look like? So a parabola on the xz, is it opening a parabola opening towards the x or a parabola opening towards the z? Think of y is equal to x squared. It'd be opening towards the z. Think of y is equal to x squared.
The height of the cylinder will be the x.
So on the xz plane, it would be opening towards the x. Right? So that's what it's opening towards, the xz plane opening towards a positive x. And then now we're going to sweep it along the missing variable, which is the y. So this is harder to draw because of the angle that I have it in. Okay? Then you can just y z is equal to 1. Those are hyperbolas with the asymptotes on the x and or the y and z axis. So you can just draw them. I'll draw that using a computer. So y times z is equal to 1. So if you look at it from up along the x-axis, let's see, this is the x-axis right here. Where's the x-axis? This is the x-axis. If you look at it from the x-axis, it looks like the y is going down, the z is going to the side, to the right side. Then it looked like those hyperbolas, like 1 over x graph. It's a nice color. Trying to find a nice angle too to have it represented in our picture. That looks good. Okay, so these are called cylinders. Now I know we think about a cylinder like a can where it's circular, but cylinders, the definition of a cylinder would just be a graph that's being swept. So this starts off as a parabola, but then when you sweep it, it becomes a cylinder. So we can think about this as a parabolic cylinder. So a cylinder in general would be something that's going to be swept along an axis. Now whether that be the x or the y or the z axis, or it could really be some other weird axis that, like a line going in a slanted direction. But in general, that's what a cylinder is. These are started off with hyperbolas on the y z plane. And then they turned out to be cylinders, so I would call this hyperbolic cylinders. And then these are just circular cylinders. We can also have elliptical cylinders, right? There was an ellipse that had been swept. Okay? Cool? All right. Distances. The distance between 2 points in 2 dimensions is the square root of x minus x1 minus x2 plus y1 minus y2. In 3 dimensions, you just add on that third component. So if you have x1, y1, z1, x2, y2, z2 as the 2 points, you can find the distance between them by subtracting the components, squaring them, and then adding them, and then taking the square root. Now, there's this idea of trying to describe a set of points using some sort of equation. So, one way to do this is what they talk about in the textbook. Let P1 equal to X1, Y1, Z1 be fixed. And then let X, Y, Z be arbitrary points. So if we use this idea of a distance from a fixed point, and then we fix the distance what we can do is we can fix the distance from that fixed point and then try to see what kinds of graphs are we going to be able to describe. Think about this as, let's say, anybody in the VR club? Say you're in the VR club and you're fixing your center, your chest as the fixed point. And then, can I finish? You have a fixed point in the center, and then you have the VR thing in your hand, right? So you're taking that VR control, and then you're swinging your arms any way, any direction, as long as it's the tip of your hand is the same distance wherever you rotate, whichever way you rotate. What do you think you're going to end up drawing? A sphere, right? So you can spin around in a circle, you can tilt your arm around a little bit, and then you can continue to spin around. But regardless of how you spin, what you're going to draw, what you're going to end up drawing are pieces or drawings that are going to be on a sphere, centered at this point. Okay? So if we put that in this equation, this is your fixed distance, d. So let d be some fixed distance, is equal to, now we want to find the distance between these 2 points, x minus x1. Now x is arbitrary, so these points over here are going to be every single one of these points that you drew. Plus. So if you work this out and take a square both sides, then you can have the x minus x1 squared, y minus y1 squared, z minus z1 squared is equal to the radius squared. I guess I should have used r, because d looks like a diameter, but it's not. So you got x minus x1 squared plus y minus y1 squared plus z minus z1 squared is equal to r squared. So we have an equation of a sphere. This will be handy for us later on because we're going to be asked to describe spheres, write equations of spheres, and represent spheres using x, y's, and z's. And then I need you to be able to distinguish a graph that looks like a cylinder versus a graph that looks like a sphere. Okay? All right, I think that's it for today. See you guys next time. Bring your little cards so we can play around with it. And if you forget them, you might not get credit for it.